All good? All right. Thanks for the intro. I'm thrilled to be here at the Joint Research Center workshop, and I thought it would be a good idea to tell you about Project Everest, which is a very large-scale, long-term collaboration between Microsoft Research, Inria, and other academic institutions. So Project Everest started in 2016, and the motivational goal was to look at the software stack that powers secure communications on the internet and see what we could do about the sorry state in terms of bugs and flaws of that software stack. And so rather than tell you everything about Everest, I'll just give a little bit of background and then spotlight 3 recent achievements that I hope will get you excited about the joint work that we do with all of our partners. So one thing to mention is that I'm one speaking for many. We have many people in Project Everest, ranging from 3 Microsoft Research Centers to several long-term collaborators at Inria Paris, and many alumni and people in other research centers. It's really a close collaboration. I'm the co-PhD advisor of several of these folks, so it's really a long-term, very tight collaboration between Microsoft Research and Inria. So a little bit of motivation. If you look at the software stack that powers, say, secure communications on the internet, when you go to an HTTPS website, it says there's a lot of bugs. There's bugs in, say, the parsing, or there's bugs in the math that's powering the cryptography at the bottom of the stack, or there's bugs in every sort of cryptographic library. And I could fill several slides with all of the bugs that have been found in the set of software that's using that powers secure communications. There's been like dozens and dozens of bugs in OpenSSL. There's been all sorts of bugs, and what I find personally fascinating is that there's bugs at every layer of the stack. You have incorrect parsers, you have incorrect cryptography, you have wrong math, you have buffer overruns, you have incorrect state machines. It's like a wonderful cornucopia of every kind of possible bug you can think of. And so Project Everest was started in response to that. Seeing that the communication software is so insecure, we said, okay, what can we state? What can we do? And so the answer, what we use in Project Everest, is formal verification. And formal verification allows us to formally prove certain classes of properties about our programs with mathematical certainty. And these properties of interest might be things such as memory safety. My program has no buffer overflow, or functional correctness. My program is always computing the right math. When I do a modular operation somewhere in a finite field, then it's always correct, no matter how much I optimize my code or how smart I try to be with my little math. We also have like properties of interest, such as side channel resistance. I'm never going to branch on secret data or use secret data to access memory. And then there's more high-level properties, such as cryptographic security and authenticity and confidentiality. And so, equipped with the tools of formal methods, what can we do? What can we state about the secure software stack? And that's the whole raison d'etre of Project Everest. And so we've been going on at it since 2016, and I would say that we've been trying to focus on 3 fronts. There's both the foundational aspect of developing new tools and new languages to make this endeavor possible, and that revolves around Project F-Star, whose center of gravity has historically been in Redmond. We also have focused on applications, trying to find new verified software that would be relevant, such as the Hackle cryptographic library, the TLS record layer, verified optimized assembly code through the Veil project, Quick, the new communication protocol, Noise that you heard about from Sean a few talks back. And the third front that we've been trying to hit on is the deployments. Deployments are happening now, and code from Project Everest has been used in numerous well-known existing pieces of software. If you're using Firefox, you're using the NSS the NSS cryptographic library, and the cryptographic library that powers Firefox. 25% of their code is now verified, and it comes from us. Another piece of software that you might have heard about is the WireGuard VPN. And on Linux, it uses EverCrypt's implementation for Curve 25519, a cryptographic algorithm. The Tezos blockchain is using code from us, a lot of code from us. The ARM embed toolchain for embed is also using it. Windows is now featuring several pieces of formerly verified software coming from Everest, notably an implementation of Quick and some parsers for the VM Hyper-V infrastructure. You heard about CCF from Cedric earlier, also using a little bit of code from Everest. And another project that has recently adopted Everest code that I will talk about in a few minutes is Election Guard. One thing I mentioned is that we use the F-star language all throughout, and the F-star language has a variety of backends that allow us to generate, among other options, x86 assembly and C code, and that has historically what has allowed us to drop code into existing software project, because if we hand off some mixture of C and assembly to people, it's very easy to drop into their existing software, and that's how we ended up with so many integrations. And so what I'd like to do now is focus a little bit on some recent applications of Project Everest. So where are we standing now? Project Everest is kind of like a pyramid. We've been working our way up throughout the years to have a completely verified software stack. Initially, we started with the cryptography, the core individual cryptographic algorithms that are at the bottom of the stack and that are kind of the foundation of everything else. If you get those wrong, then you have everything wrong. These are the Hacklestar project and the EverCrypt project, which generate optimized C code and optimized assembly code, respectively. A couple years after that, we started looking at unifying C and assembly together under a single abstraction called EverCrypt, and I will talk about that a little bit. We also started looking at parsers in 2019, and we continued to move our way up the stack. For instance, in 2020, we wrote about the Quick protocol and how to combine verified cryptography and verified parsers and serializers to implement the Quick record layer and packet encryption. And most recently, we've been jumping even higher up the stack and looking at not just individual cryptographic algorithms, but higher level concepts such as a state machine or a peer management library with linked lists and like hash tables through the Noise Star project. And each one of these boxes has properties of interest because the toolchain that we use is very versatile, and we can prove things such as side channel resistance for the crypto. But then when you're at the other end of the stack at the top, maybe security levels that Sean told you about are more important and more relevant in terms of user-facing guarantees. I won't talk too much about Noise Star because Sean already covered it, but the message I want to send is that we're no longer spending our time on individual crypto. We're spending our time on much higher levels of the API. So Project Everest continues to make forward progress and to reach on and on to more advanced layers and to work its way towards a complete verified stack. And the other thing that I want to highlight in the Noise project is that we are also learning how to scale the art of writing a large amount of verified software. Sean told you about how there was one verification result for 59 different Noise protocols. And I think that's really the culmination of a long arc of work that has been going on for several years between Inria and Microsoft Research about how to improve tooling, languages, and techniques to make it easier to verify large pieces of software. And if you look at metrics like the proof to code ratio, how much proof you have to write for each line of code that you get on the other end of the toolchain, we can see that over the past few years, because of the tight coupling between people who write applications and people who work on the languages, we have achieved much better productivity. And this is a collaboration with several folks at Inria and Abhishek, who's also in India. Another project that I want to give you an update on is EverCrypt. EverCrypt is the unified crypto library that offers both C implementations coming from the Hacklestar project that has been developed and driven by Inria, and the Veil project that offers optimized verified assembly. EverCrypt has a collection of algorithms you can see on the right for all of your cryptographic needs. It has formal guarantees such as side channel resistance, memory safety, and functional correctness. And I like to call EverCrypt industrial grade because it has several features that you need when you're trying to have a solid crypto library to integrate into your project. The performance is state of the art, and our verified code is, for some algorithms, as fast or even faster than unverified code. The library will automatically pick the best implementation for you, and will do so by automatically detecting what kind of CPU the code is running on. And the library also offers high-level APIs. And so one recent application of EverCrypt, among many, but one that I'm particularly excited about, is Election Guard. Election Guard is a toolkit that allows end-to-end verifiability of elections. It's not like a whole system that you just drop into a voting machine. It's an SDK that vendors use to provide verifiability. The properties of interest when you're using Election Guard are privacy. Only you should be able to know what you voted for, and no one can decrypt the result of your vote. But also the other counterpart property is integrity. You want the ability to verify that not only has your vote been correctly recorded, but has also been correctly counted, correctly tallied. And the idea is that the counting cannot be flawed, because otherwise it would be, if only a few people verify that their ballot has been properly counted, then it would be detected statistically. And so when you hear these properties, well, you realize that Election Guard is using homomorphic encryption and asymmetric cryptography at its core, and they were very happy to use EverCrypt to provide a stronger even guarantee that their implementation is bug-free. And this has been a very productive collaboration with other folks at Microsoft, such as R.C. Carter and Josh Bonallo, but also various people associated with the Joint Research Center, such as Santiago in MSR Cambridge and Marina at Inria. And one achievement that made me particularly happy was that recently the US House of Representatives conducted their leadership election. The Democratic caucus of the US House of Representatives conducted their leadership elections, and they voted with their iPhones using a voting software that incorporated Election Guard and thus EverCrypt. And so the Assistant Speaker of the House was elected by electronic remote voting using verified cryptography, and I think that's a huge first. Okay, I only have a few minutes left, so another recent achievement of the EverParse project that I want to highlight before I wrap up is our technology for verified parsers and serializers called EverParse. The idea is that you have a lot of network formats that are out there, and that oftentimes people are just taking bytes from the network and casting them to a C-struct and hoping that everything goes well after that. So oftentimes, like, input validation and guarantees are very minimal, and that's another essential part of the stack. And so I think EverParse and EverCrypt have that in common, that they were key stepping stones on the way to a fully verified secure communication stack, but they found very important use cases of their own. EverCrypt ended up being integrated in a variety of projects, and EverParse too found a lot of applications, not just for verified communication channels online, but also for many other pieces of code that need to deal with network formats. EverParse is a framework, and it will auto-generate parsing code that is safe, correct, and zero copy, based on an input description that you can see in the top right, which is a input format that kind of resembles C-struct declarations, but spiced up with additional properties such as refinements or actions that need to be taken upon successful parsing of one of the fields. And with that description that you have in the top right, through EverParse, you get not only a formal specification, but also a low-level implementation using the Lodestar technology. And you have theorems of that come for free systematically when you use the EverParse technology, such as if you serialize something, then parse it, you get the same thing back. And if your message was valid in the first place, you can serialize it after parsing it, and you get the original message. The performance is excellent. We have noticed significant performance improvements, and one thing that has really worked out is our collaboration with Windows. and in particular with the Hyper-V infrastructure in the Windows kernel, which is the isolation technology used to run multiple VMs on the same machine. We've made significant progress, and since spring 2020, every network packet passing through Hyper-V has been validated by EverParse. It's not just C and C++ clients. EverParse, just like EverCrypt, can be used from existing software or can serve as a stepping stone to author even more verified software. And so EverParse has been used for other Everest projects, such as the TLS 1.3 record layer, the Quick record layer that I mentioned earlier, and many others, all the while producing verified high-performance C code. And this is a collaboration with Tahina, Nikhil, who are in Redmond, Cedric and Antoine, who are in Cambridge, Nadim, who used to be in RIA when he started this work, and many other folks. I think I've reached the end of my time, so the message that I want to leave you with is that verified secure transport can happen now. We have seen verified software used in the real world. It has been a wonderful Microsoft Research Inria collaboration that has led to a lot of synergies between the two institutions, and it has allowed us to improve the theory and practice of software verification over a multi-year project that is still ongoing. And with that, I'll be happy to take any questions.